But let's get started. So, welcome everyone to Nice Review Stream Day 2. We're going to go through quickly all 4 problems of this contest, and yeah. So, starting from problem 5. So, for those of you that don't know, this is defining the original problem, but for my purposes, I like to use the notation that is correct. Fp cross denotes the set of non-zero residues modulo p. So 1, 2 through p minus 1, if you will. And this problem is asking for all the primes p for which there exists a function such that this thing is true. And the first thing I should say is some people will be talking about primitive roots. If you go on the forum, people will be talking about like primitive roots, blah, blah, blah. And the reason is that as written, this problem doesn't really care about the addition structure of Fp. Like, it's purely a multiplication problem on the non-zero residues. So, like, it would be equivalent to have a function g from z mod p minus 1 to itself, satisfying g plus g of n plus g of n equals 0 mod p minus 1. You could, if you know what the primitive root is, translate the problem so that it looks like this. However, we're not going to do this because we don't need to, but I'll comment a bit later. But it's sort of like the problem only uses one operation, and if you know this, you have a good reason to suspect the fact that p is prime is probably not important beyond that, because there's no nice property when you take mod p minus 1. Like, this thing does not have any promise about the set of prime factors or whatever it can have. Basically, about the only thing you're promised is that it will probably be even, and that's it. Okay, so let's go to the solution. So first, f is a bijection, and the reason is because f has an inverse function, namely n equals like fn over ffn. So given, I guess this is a way of saying like, this will show that f is both injective and surjective, because you can recover n from f of n, and also like, well, that's n. So, cool, f is a bijection. And so what that means is, well, sorry, there's a typo here, let's just say g. If I take this thing and straight multiply it across all inputs n, each individual thing will get through all of the p minus 1 residues. So what I mean by this is product of n of, well, for example, like product of n is just like p minus 1 factorial, but also product of n of f of n will also be p minus 1 factorial. That's what it means to be a bijection. And also, f of n, for same token, would be p minus 1 factorial. So multiply all together, and you get, what do you get? You get 1 equals p minus 1 factorial cubed. And also, however, there's a theorem that's called Wilson's theorem. And Wilson's theorem says that p minus 1 factorial is minus 1. Hence p equals 2. Is necessary. It's also sufficient because f2 cross has only one element, so there's only one function and it will work. So conclusion, answer is p equals 2 only, with the construction being trivial. So that's all of problem 5. So I promise I go and touch a bit again on these primitive roots, and if you did this, you probably got basically the same situation, except instead of quoting Wilson's theorem, what you will quote instead is the fact that when you add 1 plus 2, 0 plus 1 plus 2 up to p minus 2 is equal to half p minus 1 p minus 2. Half p minus 1 p minus 2 is not equal to 0 mod p minus 1 because p is odd. So in other words, if you use the primitive roots framework, if you prefer to use addition rather than multiplication, then instead of quoting Wilson's theorem, you essentially quote one proof of Wilson's theorem, which is this fact. But if you prefer the multiplication because you don't need to quote primitive roots, that's fine too. It doesn't really matter which one you do. What are you using? Yeah, check the link that Massachusetts put. Okay, so let's move on to problem 6. Minus 1. Any triple injection. Okay, so in this thing you have a game with 2n lamps. I think the original version featured rocks or something, which is a little better actually because it's easier to do this problem if you think about them as moving around. And you start like this, so I'm drawing the case where n equals 4. And on each of Anna's turns, which, let's see, what's the... Anna is she. Okay, so she can move a 1 to a 0 like that. Actually, that's the only thing she can do on her first turn. Also for Banana, Banana either turns 0, 0 into 1, 1, or vice versa. So, I can maybe more tersely express it like this. This is what's going on. Yeah, and Anna, Banana wins if and only if she ever gets the all 0 string to appear. And Anna wins any other way. Any other time that someone is stuck. If a player can't make their move and it's like not the all 0 situation, then Anna wins otherwise. So Banana has a pretty hard task. Like it has to be on Banana's turn, all zeros. That's the only way Banana wins. Otherwise Anna wins. Okay, so let's do the easy half of the problem first, which is, anytime you have something like this, like probably there's an invariant that will just kill off a bunch of the n. Like it would be it's almost impossible, honestly, to design a problem that looks like this, where like an invariant doesn't solve at least one case. I say that now, I know I'm going to immediately regret it because someone was going to find a bunch of counterexamples, but you should always turn an invariant and you sort of expect it to work like, in some cases. You would have to be very unlucky for the invariant to solve literally no values of n. So obviously, like, one obvious invariant is called number of rocks. Sorry. The version I got had rocks in it, but it should be lamps. Let me just say number of ones. Actually, no, you know what? Screw it. We're going to use rocks. Because it'll be more useful later on. So 1 equals rock, 0 equals no rock. And you can pretend that these things are like, I don't know, these are buckets or something. Okay, so the number of rocks is a thing that only changes. It changes by one every of who changes it? Anna's turns, and doesn't change otherwise. So that is one example of an invariant. Another thing you can look at, which people are talking about JMO 2019 because they also had a similar idea, which is sum of rock indices. What I mean is, like, for example, in here, the number of rocks initially is 4. So the number of rocks is 4, and the sum of the rock indexes is 1 plus 2 plus 3 plus 4 equals 10. And this changes by 1 every person's turn. Why does rock count change on Anna's turn? Sorry, I'm stupid. Ignore. Number of rocks. Parity never changes. Sorry. Wow, that was... That's very embarrassing. Okay, sorry about that. Yeah, parity never changes. So this already implies that n has to be... Yeah, n has to be even, because otherwise the number of rocks is odd always, and so there's no way banana wins. As for the sum of rock indices, it changes by 1 every person's turn. So in order for banana to win, one plus 2 plus up to n must be even. That's the other, like, obvious parity invariant. So this will imply... Together, these two things tell you that n has to be 0 mod 4 for this to be possible. So to reiterate, there's a very obvious invariant, which is just the number of rocks, parity never changes. There's a slightly less obvious invariant, where the sum of the rock indexes always changes. And so... Conclusion: 4 divides n if banana wins. Sorry. Yeah, changes by 1. Yeah, parity changes by 1. I guess parity changes is more accurate. So this one never changes. This one always changes. Whoop-de-doo. Evan, is it true that if you do not make mop, you go to jail? I think this doesn't sound correct. I don't think there's enough jails in the country for that kind of situation. Yep. Okay, so now the main part of the problem is showing that if 4 actually divides n, then banana has a strategy. So let's make a strategy for banana. So the game starts, I'm going to use n equals 8 for illustration. So this is going to be a big table. Okay, so the first turn of the game is actually forced. Anna must move here, and everything else is the same. Okay, and what banana is going to do is banana is going to take out these 2 rocks here. Those 2 at the very back. This is possible because n is at least 4 to be divisible by 4. Okay, and what we do after this is, afterwards Anna makes some move. For example, Anna might move here or might move there. It doesn't really matter. But what we always do from now on is these ones I'm going to keep in blue. And banana always has a gap of at least two things here because banana empties this thing. So for the leftmost one, there's always this gap here, and suppose that after some while, let me just make up a state. 10, 0, 4. Like suppose we're here or something. I don't know if there's actually a possible state. But there's always these two. Banana is going to always alternate between changing these things. So on some turns, she'll add 1, 1 to the left of whatever banana did. Then on the next turn, banana will remove it. So let me write out a couple turns for concreteness. So 1, 1. Let me just erase all this. So on each of banana's turns, there's this stuff at the end that's just kind of switching on and off, like that. And then, so what this does is that because we're always banana, whenever she inserts new rocks, she puts it to just to the left of the leftmost one. So Anna can never use these because they're blocked. So from Anna's perspective, these two ones that we keep putting on and off don't change. And so what Anna is doing is she's just very gradually moving the other n-2 rocks. It's actually exactly n-2, and this will matter. There's n-2 rocks, and she's just slowly moving them from the left to the right. Meanwhile, banana is just, turning these two ones on and off. And as they go, dun 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 dun, as the rocks slowly move, the ones might slowly move as well. So after a while, maybe it's like here, 0, 0, 1, 1, whatever. But it doesn't matter. The point is that the other 6 rocks are just moving, and banana is doing something that doesn't interact with this at all. So fast forward several turns. Eventually, for parity reasons, we will reach a situation in which there are exactly n-2 rocks at the very end, and it's banana's turn to go. And if you check the invariant will promise that on this turn, it is currently 0, 0. So whatever just happened. So Anna just did this. So if banana is dumb, they're going to keep following the strategy. Up till now, what she's been doing is turning things on and off. So according to the algorithm, the next thing she should do is this. However, we're going to change the algorithm so that at this very special state in which all n-2 things are here, rather than putting 1, 1, we go to the second phase of the algorithm. And that phrase is called, let me make sure I get this right. Leave 2 things here. And then delete this one. So here there are now n-4. There's now n-4 things here, and there's 2 here. And now Bob changes. Did I say Bob? Banana. Sorry, I got both your name and gender wrong. That's embarrassing. So now maybe I shouldn't have used 6. I'll draw a bigger example. We have 1, 1, 0, 0, and then 1, 1, 1, 1, 1, 1, 1, 1, for example. Hang on. I messed something up. 6, 2. This is n-6. Okay, so this is not a valid example. For n equals 12, I should have 6 things here. Okay, so now Anna, again, is sort of forced. Anna is now moving these. And it's going to take her a while for those ones to reach a point where they're stuck. Nemo hits Evan now? Wait, what? Yeah, so now on each of Banana's next turns, the strategy is take these two on the next turn, take out these on the next turn, take out these on the next turn. So with all these rocks that are stuck on the end, we made a gap of 2 here that Anna is, slowly moving, and then we start wiping out all these rocks from left to right. So that makes things very easy. So now there's just 2 ones. And, they're wherever. And now that there's 2 ones, again, Anna isn't going to get stuck anytime soon. So we go to what's called phase 3. This was phase 2. Phase 1 was the part where we got to here. Phase 3, Banana goes back to what she was doing before, where she keeps toggling 0s and 1s to the left of the leftmost one. And the point of, again, doing this is that, Anna can't do much about these, because these rocks are just stuck, and they kind of go up, on and off, all the way until, sort of like before, these ones just slowly move over, and sort of, again, for parity reasons, what's going to happen is eventually you end up at a state that looks like this, 1, 1 at the very end. Hang on. Yeah. Okay. And now, again, for parity reasons, this will happen with a 0, 0 here. So finally, Banana can remove them. So I call this phase 4, but it's really one step. It's just remove the last 2 things, and it's fine. So this is the algorithm.
Never mind. Are you done yet? Sorry.
Yeah, that's all I had to say.
Oh yeah. So I kind of want to talk about this. I have a little bit of a story to tell about this problem. So initially, it was just just the lamps 1 and n, not the ones in between. But when I was trying to test solve it, I misread it as all the ones between 1 and n, and so that's how the problem ended. It was the way you solve it in the previous reformulation of the problem is the same. This sort of process just turns out to always do the same thing, to some extent, but yeah.
Cool. You can just remove the 4 things at a time by leaving 3 at the end. Probably? I mean, I don't think this algorithm is at all unique. I basically think any algorithm that is not... I think if Banana picks any algorithm that is not self-destructing, as long as Banana always makes a move that doesn't immediately end the game, I think Banana wins. Basically, no matter what, for parity reasons. Either that or the game goes forever. It could be the game goes on forever because Banana just, goes in a loop. But I think it's hard for Banana to lose other than by self-destructing. However, I picked this algorithm because it was the one that I thought was the easiest to prove worked. I basically wanted to make there as few choices as possible. So I think most algorithms have this idea of putting the ones right to the left, but exactly which gaps, if any, to put them in varies depending on what the algorithm is. So this is the one that I came up with that I thought was the cleanest, where the ones just move and there's only one place where you have to change strategy, which is to wipe out most of these. Then when you have 2 ones, that's also easy to deal with. So no. And then it's fine. But there are certainly other algorithms that should work as well. Okay, let's go on to problem 7. So problem 7, I honestly think it might be easier to use the whiteboard for this because I have to make a table at some point. So nice 7 is a functional equation. And it's a functional equation that's, I would say, pretty standard. Well, let's see. So first, we're gonna do dumb stuff first. So let me get something out of the way. If I plug in all ones, what do I get? If x equals y equals 1, then 2f1 plus 1 divides f of 1 minus 1, which doesn't happen for most values of f of 1 because the left-hand side will have a larger absolute value. And I think the cleanest way to deal with this is let's just double the right-hand side. We'll eat that loss. So divides 2f2 minus 2, and hence 2f1 plus 1 divides 3.
1 plus 1 divided by 3.
No. Echo, stop. So hence f of 1 is I don't know, minus 2, minus 1, 0, 1? I think. Okay, yeah. On the other hand, if x equals y, like, you know, the situation is like basically just as good. In general, if x equals y equals, I'm gonna say p first, but the logic is really a little backwards. You don't decide that p should be a prime until after you see what happens. But you can do the same thing. So 2fp plus fp squared divides pfp minus p cubed. Okay, so let's just take the doubling. So the pfp. And you do this thing. I call this remainder bounding, but I don't know if other people have a name for it, where this 2fp is congruent to minus p cubed, or minus p squared mod the thing. So this is like, hang on. Yeah, is minus 3p cubed. So it's almost the same as the equation from before. I mean, actually it's the same thing except here I plugged in p equals 1. But the reason you pick p prime is because that way you know what the factors of the right hand side are. Shout out to IMO website for being stupid and not loading. Which, very sad. Okay, so as I said, like, well, yeah, there's like, oh jeez, that's actually a lot of cases. Well, what's going to happen is that you get some constraint, right? F of p turns out to be, no. Okay, so what are the possibilities? Oh, that's actually worse than I thought it was. So, minus p squared over so k p to the e, where, let me call lambda, where lambda divides 3 and e is like, I guess 0, 1, 2, or 3? Oh, Jesus. So naively, there's like 16 cases or something. There's a lot. Okay. So what's going to happen is, well, so for every value of p, it falls into an entry in like a certain 16 by 4 table, where there's 4 cases for f of 1. Like f of 1 could be minus 2, f of 1 could be minus 1, f of 1 could be plus 1 or 0, and f of 1 could be plus 1. On the other hand, on the left, there are like a bunch of different possibilities, right? So it could be f of p. Let me write just a few. F of p is equal to, I hate this. There. Well, I'll go from the top to bottom. 3p cubed minus p squared over 2. F of p could be equal to 3p squared minus p squared over 2, or equals to p squared. And then so on. There's like 16 entries here, right? So there's 16 cases here. And there's 4 cases here. So basically I have this giant 16 by 4 table. And each of these tables gives you a statement if I plug in. What we're going to do is we're going to plug in x equals p and y equals 1. And when I do this, every table will say each cell of the table will correspond to some statement. For example, if I'm in this cell, if f of p is 3p cubed minus p squared over 2 and yep. So let's see if I can do this. I don't know if I can do this. This might not fit. So the right hand side is, so it's p times 3p cubed minus p squared over 2 minus 1 is divisible by minus 2 plus p plus 3p cubed minus p squared over 2. So this is like the first cell of the table. For example, and then there's 64 more cells. So yeah, we have 64 cases. Okay, so how is that supposed to help? So let me explain. There are many primes. There are infinitely many prime numbers. So one of the cells of the table, by pigeonhole, some cell happens infinitely often. One of the 64 cells has, a lot of things happening in it. A lot of primes happening in it. However, for that to be true, let's say, for example, that I was told that this cell happened infinitely often. If that's true, what I can do is I can view this as a polynomial in P. And when I do that, there is a quotient and a remainder, right? It will tell me that like the left-hand side divides the right-hand side, which is maybe equal to like some quotient plus some remainder. However, what that kind of forces is that because like you take P big, this thing is much bigger for large P than the smaller degree remainder. It divides this, so we don't care about it. So that implies the remainder has to be 0. So whatever cell happens infinitely many times, there could be more than one, but we know there's at least one cell that occurs infinitely many times, and whichever cell that is, the statement that's written in it has to be true as a polynomial relation, not just like as a statement for certain values of P. The left-hand side must divide right-hand side as polynomials in P. Okay, so basically what we're going to do is now show that most of the time that's, like, you look at this and like most of the time we're like, no way, right? Like the left-hand side is like this random convoluted thing. Like why would it divide the right-hand side unless it's a solution? So let me do a little bit of optimization, but probably not do all the details. So, first of all, f of 1 plus f of p plus p divides, let's see, what is it? P of p minus 1 is the same as saying f of 1 plus, we'll get rid of the fp part because we think that's the high degree part. F of p plus p divides, so it's going to subtract off p times. Boom, boom, boom. Okay, and then everything's negative, so we'll just get rid of the negative part. 1 plus p squared plus p times f of 1. So this is what we're looking for. It's a better way to write the relation we're looking at. And what this already tells you is that when you look at this degree is like less than or equal to 2. So already this will like kill off. Let me not write it. It will kill off this entire row, for example. So this whole row is not going to work because this FP is too high degree. Ugh! What the heck? Yeah, that whole row is going to die because 3p cubed is degree too large. Isn't degree of FP at most 3? No, what I'm saying is that for this statement, for this box statement to be true, the degree must be at most 2. We're saying that this thing divides this. This guy is degree 2. So that forces this thing to be degree less than or equal to 2. Yeah, and then similarly, you can do a lot of other stuff. Like you can plug in values of f of 1 and then look at the constant term, and you'll see the constant term is not going to work out either. Right, because for it to divide as polynomials, this is constant term 1. This is constant term f of 1. So if you wanted to divide as integer polynomials, well, guess what? This f of 1 better be plus minus 1, or maybe 0 is possible too. So that means this whole column where f of 1 is equal to minus 2 is also just no-go. So in this way, you kind of just like, you have this 64 cells, but already I've managed to remove, bring it down to 36. Why does it have to divide as, it could divide as a rational, is that something I have to worry about? I see, if it divides as a rational polynomial, it could still have integer quotient. Is that true? That feels really weird actually to me. Yeah, you're right. You are correct. I think I have to like look at the leading coefficient as well. So FFP is like leading coefficient like ugh, dang it. Right hand side is a degree 2, left hand side is oh, that's lame. Sorry, you're right. This constant term is a little more finicky than I thought. Can we like first prove f is 0 equals 0? Yeah, that's sort of the general approach. Sorry, f of 1. Wait, now I'm confused. Anyways, to be honest, I didn't prepare the cases because I didn't want to. It seems super annoying. But the point is that like each of these you can just look at and you blow up as many like in bulk as you can. You can probably do this. F of 0 equals 0 could help maybe to make your life a little easier. Let's see. F of 0 is supposed to divide 0. Yeah, f0, 0. Does that help me? If I plug in like 0, 1, does that remove some cases for f1? Yeah, f0 equals 0 for sure, because what you get is f of 0 divides 0. And I'm trying to think if like 0, 1 or 0, p might decrease the amount of casework. 0, p actually seems pretty good. F of p divides p cubed. Did you guys give me the solution for positive numbers? F of 0 equals 0. Oh, sorry, never mind. F0 divided 0 does not imply that F0 equals 0. Whatever. Do you guys actually want me to do the case work? Because I don't actually want to do the cases. I think I could probably, I think in principle, okay, yeah, that's actually a good idea. We'll do a democratic. You want to just factor out? Yeah. Oh my god. Okay, good enough for me. Alright, lucky break. Yeah. I think the hard part is getting the cases to there's probably some difficulty in getting the cases to be not too many, but also there's not that many cases once you get rid of the obvious ones. That's a little borderline whether I was going to do it or not. Okay, so once you know that, what you'll find is that there's only two cells that could actually happen. One of them is f of p equals p squared, and f of 1 equals 1. Or f of p is minus p squared, and f of 1 equals minus 1. So these are the two that survive after you do the case analysis, unsurprisingly. That problem is... Yeah, the dummy unit has no problems, unsurprisingly. Okay, so now what we're going to do is like, okay, well, without loss of generality, let's suppose we're in this case. The other case should be exactly the same by, I don't know, just negate f or something. Well, I'll just do the first case because I think the other case is the same. So what we're going to do is like let x be anything. And then let p be big. And then we'll plug in... Sorry, let me call it y so that I don't change the names. I think y is better. No, sorry, I actually want x. X. Okay, so f of x plus p squared plus p squared times, sorry, p times x is supposed to divide x f of x minus p cubed. Should I have done that the other way around? We'll just try both of them. One of them should work. Okay, so we'll do the usual where we're going to subtract all of x times the thing. F of x plus p squared plus p times x divides, let's see, x times it, right? So p squared times x plus p squared plus p cubed. The heck? No, what? X. It's supposed to be p times x squared. There we go. So this is equal to p times x squared plus p squared plus px. And now I can subtract another copy. Poop. I feel like I've done this exact calculation before in 2016 N6. Like I feel like it's actually the same expression too. Okay, so yeah, you just let p be big. If p is big enough that p doesn't divide this guy, then you can kill off this p, and so this thing has to equal 0. So x squared is fx is x squared. The same is true if you, and the other case is similar. So once you have it on sufficiently large primes, you'll have it for everything. The end. Yeah, remainder bounding for sure. Why is every NTFE like? I don't know, remainder bounding is so strong. Yeah, not all of them are, but I think a lot of the divisibility ones are. Like the ones where you have like some random expression divide some other random expression, and then like there's some things that have F and then some things that don't. A lot of them just end this way because like remainder bounding is good. Yeah, like it's because of the divisibility, right? Like because you need to be able to somehow get an equality out of a divisibility, and this is hard. And one of the ways to do it is that by using left hand side bigger than right hand side, so right hand side equals 0. If you have a functional equation that's like blah equals blah, then I don't think it's as necessary that something like this will show up, because you know you already have the equal sign in your problem. But when you have a divisibility thing like this, you don't have any equal sign. So in order to solve a problem, you need to get an equal sign to show up somewhere. And, well, remainder equals 0 is a pretty good way to do it. Okay, MathChew, did you have, or Chenis, did you either of you want to say anything?
Sure. So, the way this problem, or this devil spawn, came into existence was... So, most normal Olympiads, like, most people know that normal Olympiads have like 6 questions. But we decided to have 8 questions for some reason, which I'm not sure of yet anyways, but, so, we kind of like got day 1 down, especially after we got the Nikolai Belohov problem for 4, which was really surprising. So basically, we were kind of unhappy with like around the problems around like the 6-7 area, because we kind of didn't have much stuff there. Like basically we had a problem that was around the right difficulty, like in that area, but one that wasn't. So, you know, I also was like slacking in NICE for basically the entire time. So I'm like, maybe I should pull my weight. So I'm like, okay, let's do a problem. Let's just write a problem. And like, very recently I did some, or recently when I wrote this problem, like before I wrote this problem, I did a lot of NTFE. So I'm like, okay, I have this concept of remainder bounding. Like, if I try hard enough, I can probably get a problem to exist. And people can just hate it. So I just decided to go with f of x is x squared, and then I try to like get that to work. And then I realized, okay, f of x is x squared like does not seem to be... The original problem wasn't this, by the way. It was like something like f of m plus mn divides m cubed plus nf of n. Something like that. Is that right? I don't remember. Should be on the... Should be on the thread somewhere. Okay. Yeah, the original problem was find all functions such that this weird condition held. Yeah, actually, yeah, that's it. Identical to what I typed up. Okay, so that ended up being minus x squared. And so it was there. And then I had a solution where I basically did the same thing that was done on stream. I'm just like, okay, I'm lazy. I'm not going to do all the cases. I'm just going to like hand wave it. So I hand waved it and like I said, okay, it is very easy to check blah blah blah. And the hilarious thing was that I said it was very easy to check blah blah blah. I never actually checked it and I was wrong. So my entire bash was like just wrong, and I had to finish like a couple of cases that ended up being non-trivial. So Andrew Wen ended up solving the last part of the original question with, I think, f of 1 p minus 1, which kind of like just deleted the entire problem. Besides like the whole, you know, the finishing part where you just let p be big prime. So because the problem ended up getting deleted by one thing, I'm like, okay, well this is not great. So we eventually ended up going through like 50, not literally 50, but like 50 variations of this problem until we settled with something that was basically isomorphic to that problem statement that's on the screen right now. And yeah, I think that ended up well, especially because f of 0 is non-trivial. So that's how this mistake came into existence.
Also, we got a submission that was like, we have 2016 N6 at home, and we lost it. Like, when we read it, we were all like, we started laughing. It was too funny.
All right. Okay, so let's do the number HGO. Okay, I'm gonna start by drawing. All right. All right, so I'm gonna. All right, triangle. Triangle I'm gonna draw. I've drawn all the midpoint things and things. H is triangle center. ABC3 versus ABC4. M is the midpoint of BC, and you want to show HIM is 90 if and only if AB plus AC equals 2BC. Alright, first let me get rid of AB plus AC equals 2BC. The following lemma is known. Lemma HMM 2013. AB plus AC equals 2BC if and only if I is midpoint, the midpoint of AIA. And this is pretty direct to prove. This is called, you use Ptolemy's theorem with the fact that IMA equals BMA equals CMA. If you use Ptolemy's theorem together with this and see what you get, it will be exactly the lemma. So actually, I'll format this so that the whole thing is on the line. So at this point, if you don't like geometry, you have a way out already. Because what you can do is you can use any coordinate system. I think the one I have in my head is oh crap, now I wish I had my iPad out. Yeah, so basically what you, if you want to use a complex, what you probably do is something like, which thing? We're gonna use x equals MA, y equals MB, z equals MC. Those are, so the orthocenter will be the kind of weird one. if I use this coordinate system, the orthocenter is the sum of ABC, which is minus yz over x plus zx over y plus xy over z. Meanwhile, I equals x plus y plus z, m is y plus z over 2. So AB plus AC equals 2BC, according to the Ptolemy thing, is equivalent to let's see, x plus y plus z times 2 is equal to x plus minus yz over x, or something like that. So that's one condition, and then what you do is you just grind out the condition for HIM equals 90. If you do this, what will happen, you will find that it's equivalent to x plus z, y plus z squared, x squared plus 2xy plus 2xz plus yz equals 0. I'm not going to do this calculation because I'm not going to use this solution, but I'm just outlining this so that people know it exists. Yeah, you have to expand and factor, so it's not pretty. You can do it by hand in like not too long, but it's not easy, I think. Anyways, this thing happens, and then this is the main term. It's a rearrangement of this. The other is all factored out because your arc midpoints are never diametrically opposite. It's about, I think when I checked it, it was about 60. It can tell how many terms it is, right? From looking at this, it will be 4, 8, 16. It's 64 terms. So, doable but not fun. I probably wouldn't do it on a contest unless I was running out of ideas. Well, maybe I would actually. I'm not sure. If I had like not much time left, I probably wouldn't. If I had like 3 hours left, maybe I would be like, I think I can expand 60 terms in 3 hours. It's not super hard. Well, I think you like, when you look at the actual expansion, a lot of the factors I think are kind of clear. Like you'll see an x plus y factor just through it, and then by symmetry x plus z should also be a factor. Or something. It's not very hard to guess the factors, I think. Especially because you know this bracketed term, this main term should be here. So if you divide out by that first, you're left with something which is like, you know, as long as you get one of the factors, and it's not hard to guess, you probably get the rest of the factors too. We're not going to do this. We're going to use like I said, that exclusion. So that's just for completeness. Okay, so this solution is based on what is called the Bevan point, which you may remember from CMIMC on a recent stream. I want to introduce V with the Bevan point. Bevan. So what is the Bevan point? There's a couple definitions. First is that it's the circumcenter of the light cyan triangle. That point right there. So circumcenter of the triangle whose vertices are all three x centers. But because it's defined that way, for example, you know it's on line, let me introduce ABC3. You know it's on line IO because IOV is the Euler line of that big triangle. So that V is there, and that's pretty good. The other nice thing is that IBV is promised perpendicular to AC. So this is perpendicular because this is altitude, and these guys are cyclic. IA, B, A, IB are cyclic in the circle with diameter IA, IB. So because this is perpendicular, these two are anti-parallel, so this is also perpendicular. So we're going to mark these 2 points, and I need names for them. We're going to call them, I don't want to call them D and E. Also, that point is really hard to mark. Let me perturb the picture a bit. Here, that's better. Okay, let's call them Y. Yeah, this is also Y and Z are where the X circles touch. You want E and F? Really? Okay, fine. We'll do Z and Y. Oh, crap. Okay, Y and Z. So, yeah, the upshot is that unconditionally, the circle diameter AV is pretty good. It passes through AZ and white. And AYZ. There we have it. Let's color this red or something. Yeah. So this thing is always unconditionally like this. But VIO is also the Euler line, so that's always unconditionally there. So we'll color this green or something. That's the Euler line. Anyways, this IMA, the HMMT 2013 condition is also equivalent to something, right? It is equivalent to angle IIV equals 90 degrees. Because you want IO to be perpendicular. So, in other words, one direction of the problem is equivalent to having this orange circle pass through I, like so. So that sort of gives us control, because now our AIV is 90, it corresponds to some like nice cyclic thingy. Okay, what about the other condition? What is HIM equals 90 supposed to be? So what we're going to do now is we're going to... See, the reason I save D, E, and F is because I need them for the altitudes. Alright, let's mark these. Oops. Ow. These two. I want these two. So those are altitudes. Wait, no they're not. Nah! Come on! I got baited so hard. Do I not need the... I need the midpoints of the altitudes, right? Alright. No, no. Select. Click. Click. We'll color these red because they're part of the orthic picture. Okay, are you asking me to like draw the altitudes and not mark the feet? I guess that's not that reasonable. Okay, whatever. We're gonna introduce the midpoints of the altitudes, and that one oh shoot, this is annoying. P is midpoint. We'll call them Q and R. All right, we'll keep being symmetric. So Q is the midpoint of BE, R is the midpoint of CF. And again, there's sort of something unconditional that happens because QM is perpendicular to EC because they're both midpoints, and RM is also unconditionally perpendicular here. The circle with diameter HM always passes through Q and R. So circle HM Q. So this is an unconditional cyclic quad, and the problem is saying again we want I to lie on this. So I'm going to color this red because it's part of the orthic picture. I should color this blue actually because it's part of the X center picture. So it's sort of interesting because it's like I'm sort of automatically classifying things as like circumcenter, orthocenter related versus incenter related. These two are usually not tied together that well. Right, so for a random triangle, it's saying I lies on one circle if and only if it lies on the other circle. That's what the problem wants. So the question is like, okay, that's fine, but how am I going to tie these things together? And the answer is there is a lemma. And that lemma says that these two things are lines. Oh, this is really hard to read. Did I get the lemma right? I think I screwed up the lemma. Can't be... No, no, it should be the Bevan. No. What's the midpoint of altitudes lemma say? It's like, no, it is those, right? RZ and QY. Okay, I wasn't wrong. I was like, why aren't they matching up? So unconditionally, oh, this is so hard to see. I'm gonna zoom in a bunch. There's so much going on. So let's take these two guys. These are the things that will tie the two pictures together. So those of you that read EGMO carefully might know this as the midpoint of altitude lemma, where it promises that the midpoint here, the in-center, and the point where the X circle touches are collinear. So ZIR and QIY are always collinear. And this will be the thing that blows everything up, because now we have a way to tie these angles together. Specifically, the cyclic quad here is the same angle. The green one is the same angle that's holding everything together. What I mean is that directed angle ZIY is equal to directed angle QIR. And directed angle ZIY is equal to directed angle, so blue circle asserts that ZIY is equal to ZAY, which is equal to angle A. Red circle asserts QIR, or let me do it directly. RIQ is RHQ, which is also equal to directed angle A. So, because this angle... No, typo. So because like the angles are both A here, I lies on blue circle if and only if I lies on red circle. So they're equivalent. And that completes the solution. Config G6. Yeah, probably. Probably on config, because if you put on G6 some people will use the complex. If you put on config, people recognize there's like something. Well, honest, well, nice prompts are going in. I have no idea how to motivate this. I think it's not that unmotivated. Because both the right angle, like it's not like these are random right. Okay, well, no, yeah. So both of these are right angles, right? One condition is HIM is 90. The other condition is AB plus AC equals 2BC if and only if OI is perpendicular to AMA. So I think like if you have the blue and red circles, it kind of makes sense what's going on, right? Like both conditions are equivalent unconditionally to a certain quadrilateral being cyclic. So analyze the cyclic quads, right? This is GeoGebra. I'm gonna link setup. Yeah, the Bevan point is really strong when it works, because it's one of the few ways that you can get this orthocenter picture to play well with the X-center picture, right? Because up until then, right, like all the red points and all the blue points sort of don't interact, which is sort of what you expect. Like the orthocenter of orthocenter doesn't really do much, or orthocenter of orthic. But the two green lines are sort of the linchpin. The reason you don't normally see like both an orthocenter and an in-center in the same problem is they typically don't play well together. And the green lines are what make this problem tick. Because otherwise it's a standard problem in some sense. It's just, probably it's true for just based on things for that picture. But because these two green lines are here, you suddenly have a way to translate something about the orthocenter picture to something about the X-center picture. Yeah, I think if I was doing this on a competition, I would probably just throw complex at it. What are all the mo's? The committee can say. I think they probably know better problems better than me. I just picked them up recently to do this review. This is now 20? No, really? 20? It's not that easy to complex batch, is it? Did I like miss a setup? It's short with Barry. But I feel like with Barry you have to... Maybe it's not that bad. I don't know. It sounds really annoying. I guess for Barry what you would do is you would say IM is parallel to the A Noggle line, which you can reasonably deal with. And then you just have to grind out the displacement vector HI. Is that what happens? Oh, I see. Okay, I see the Barry. Okay, this is what you do. Alright? This is what we do. No, you don't grind out HI. That is exactly what you don't do. Okay, I see the... Oh, that is clever, actually. I don't think I would have noticed that. I would have just been like HI. Alright, so we'll hide this because we don't need it. And I'll shrink this a little because we don't need it to be that big. So here's how you set up the Barry. A plus AC equals 2BC you can do fine. That's like normal. On the one hand, IM is parallel to the A Noggle line. It's the line through... It's the line through A through the X touch point. So that displacement vector is... Okay, so Noggle is S minus B, S minus C. So the other coordinate will be the sum of them, which is minus A. Yeah, minus A. Up to a constant. So it really should be this divided by A, but we don't care because we're checking perpendicularity. HI is the following vector. Unnormalized, it is 1 minus A over A plus A over 2S, 1 minus B over 2S, 1 minus C over 2S. This is using the general situation where I'm exploiting the fact that H vector is vector A plus vector B plus vector C, where I set over right here. If vector O is the origin, so now everything is sort of degree at most. Yeah, when you do it this way, you don't have to plug in the nasty coordinates for the orthocenter, and the strong perpendicularity criteria will still work out of the box. So since we're here, let's actually just do the calculation, because I think I can do this. So we are looking for the condition for which the cyclic sum of... Oh shoot, it's not cyclic. Okay, never mind. Okay, maybe this is... Oh, crap. Okay, wait. Let me not get rid of all the denominators. So 2s is... Okay, this is actually just... This is... Up to a constant, it's equal to b plus c, c plus a plus b. So s minus c... The strong perpendicularity criteria says I want c plus a plus a plus b s minus c plus b squared times the cross thing a squared s minus b plus c. Okay, so this is a degree 4 polynomial. Oh man, I thought it might be degree 2, but it's degree 4. But what I'm supposed to do is I'm supposed to full expand it and cross my fingers that a plus b minus 2c factors out. Is that what's going on? Fine. Yeah, this is much better than the complex setup I proposed. I agree. Because it's degree 4. And the complex is degree 6 and more terms. Do I actually want to expand this? I don't actually want to expand it. It looks annoying. Okay, I'll just leave it at that. Like, the point is that this will work better because it's degree 4 and you can probably just get it. Don't give in. Yeah, that's why. Okay. Oh man, I actually spent a while on this.